can help us in using this notion of contrast agnostic solutions in imaging applications. So after that, I'll be speaking about some of the previous applications. So the first one is the fast random walker. So this was done by other groups much earlier. This is about 10 years ago. Then I'll talk about a couple of applications that I have done during my PhD. So among these three, I'll definitely cover these two. The third one, probably depending on the amount of time that we'll have, I might skip some of the details, but the most important aspect is, what are the takeaways of these applications and how it can be used for other imaging applications. So that part I'll summarize and then mention a few other directions on how these ideas can be used further. So to start with, so many of us, we know that translation and rotation invariances are heavily used in images. In fact, so by translation invariance, what I mean is, suppose I have an image as you see on the left side. So even if I translate the object in the image, I still, if I want to classify this image as a particular class, it would still be the same class. So this has been very well known, and people have been, these convolution neural networks have been designed so as to utilize this particular inductive bias. So this is done with the usage of shared parameters across. So they use a convolution window, and then so these parameters are shared across the spatial coordinates. So this is very well known to all of us, and also people use other kind of invariances, meaning even if I rotate my object up to a certain extent, so this would still be the same object. So what people do is they use some kind of a predefined 30-degree rotations and so on, and then make use of this. They do some kind of a data augmentation and use this information as well while training their, the models and so on. But then one of the not so commonly used invariance is that of contrast invariance. So meaning, suppose I have an image as you see on the left side. If I decrease or increase the contrast, say if I increase the contrast, the one that you see on the right side, so this image is like a contrast enhanced version of the image on left. So whether I increase or decrease the contrast, if I am working on an image segmentation, if my goal is to obtain image segmentation, then the boundaries wouldn't change whether or not the contrast has changed. So this part, this contrast invariance is something that people have not used much. So how exactly would we make use of this contrast invariance is the main topic of today's talk. So in fact, so the question that we ask is, can we utilize this contrast invariance to improve the existing algorithms in some sense? So maybe accuracy or maybe speed. So in fact, the answer is we actually improve the speed of several commonly used optimization based algorithms. So how exactly do we do that? The answer is what we need is something called as Power Watershed framework. So before going to Power Watershed framework, I want to talk about some basic terminology that is required for modeling images. So one of the commonly one of the commonly used ways to model images is making use of edge-weighted graphs. So what people do in practice is they construct a graph out of the given image, meaning each node is a pixel, and then suppose I am working on, say, a two-dimensional image. So I use some kind of a 4 adjacency, meaning every pixel is connected to 4 other pixels, one on top, one on bottom, one on left, and one on right. On the boundaries, of course, you won't have all 4 neighbors, but that's the basic adjacency that I use. And uh, people construct some kind of weights on each of the edges. So meaning, this is to convey the fact that how dissimilar or similar neighboring pixels are with respect to the intensities or the color values, or if you are working on, say, hyperspectral images, some kind of a similarity using all your bands and so on. So this is a commonly used framework. So depending on the application at hand, people construct either a dissimilarity measure or a similarity measure. So what exactly do I mean, and how does contrast invariance translate to if I work on this particular mathematical setup? So a well-known way to use the notion of contrast is people work with the pixel intensities. Say I have a grayscale image. Simply scaling up the pixel intensities would give me a contrast enhancement. But if I work with, say, edge weights, now this boils down to the fact that if I have an original graph with, vertex set V, edge set E, and then the weights are given by this particular function from the set of edges to a positive and non-negative real numbers. What I do is I transform the edge weights such that the relative orders are preserved. Meaning, I use a composition of I transform all the edge weights such that the orders are preserved. So this corresponds to if I use a increasing function with the derivative greater than 1, that effectively means that I am stretching the contrast. Say, for example, let me just take a simple example here. So this is like a fictitious image that I have on the left side, as you see.
Shravan,
yes.
There is a question in the chat box. If you could answer that, I think it would be.
Yes.
Yeah.
Yes. So this is some kind of a gradient, correct?
All right.
Yes. So yeah. So as you see on the left side, so this is like a simple fictitious image with two objects. So the objects are kind of color coded, meaning all these orange pixels correspond to one object, and the blue pixels are another object. And the values that you see, you can. So these are like the grayscale gray values of the image that I have. So once I have an image, I can construct an edge-weighted graph like shown on middle. So this is simply the edge weights are given by absolute differences of the pixel intensities. So this is like a gradient. So these edge weights serve as gradients here. And if I want to talk about enhancing the contrast, instead of working with the pixel intensities and scaling them up or scaling them down, I simply work with the edge weights. So if I take an increasing function with the derivative greater than 1, as you see here, all the weights are doubled on the rightmost graph with respect to the middle graph. So this means that in some sense, I am enhancing the difference between, the object boundaries are kind of highlighted here. So this is something of this sort. I can clearly see the differences in the boundaries and so on. Similarly, I can do a contrast decrease as well. But the basic idea is this segmentation results that I obtain on the graph should only depend on the relative ordering of the edge weights and not the actual weights. So this is something that we want to have if I want to have contrast agnostic segmentation solutions. So there are a lot of classic graph cut based segmentation algorithms, but they deal with mostly trying to directly minimize a particular cost function. They don't take into consideration only the relative ordering of the weights. Rather, they use the exact weights. So Power Watershed framework is something that helps us in just taking into consideration only the relative ordering of weights without the actual weights. So in general, most of the cost functions that are used for image segmentation fall into a particular subclass. So here my x so x represents the set of all labels for target labels for all my nodes. So the q of x is the cost function that I associate for each. And I want to minimize this cost function, and the cost function is of the form. For each edge in my graph, assuming that I have my wij as some kind of a similarity. Here it's not a gradient anymore. It's like a decreasing function of a gradient, and I use a monotonic function here on my edge weights. And so this essentially says that if my I and j, two pixels, are very similar to each other, I am going to penalize a lot if the end labels xi and xj are very different. So this, again, this Q is a generic form. but most of the cost functions that we deal with, the graph cut variants, so they only have this pairwise, I mean, cost functions, cost function terms, which are pairwise in nature. So meaning, I mean, for every edge in my graph, I only take, the cost term can be split into several terms. The cost function can be split into several terms. Each term is just simply dependent on two different, adjacent labels. I mean, it doesn't have triplets or quadruplets and so on. So that is, it can be written in this simple form. So although my Power Watershed framework is, so this can be applicable to generic functions. Today's lecture, today's talk, I'm going to only deal with this specific class of functions. So this is because this suffices for our discussions. That is one thing. Second is, when my cost function is very nicely in this form, there are some special properties which we are going to see in a couple of slides. So the final solution, it kind of depends on a very specific substructure of the graph that I'm working on. By the way, since I'm working on images, all my images are finite graphs, and I'm dealing with cost minimization problems on such finite graphs. They are of this form. So what exactly does Power Watershed framework do? So instead of yeah.
Sravan, I have a question. Can I ask?
Yes.
So in that slide, when you said X, you said that X is labels.
Yes. Yes.
So when you say label in an image, what are these labels essentially?
Okay, so suppose if I'm working with a segmentation problem and there is only, say, one object in the foreground and rest is all background, I just have two labels. So my each of
So
xi.
if there are multiple objects, there are multiple labels.
Yes. I mean, we work with. We can do it in a recursive way. And start with.
Yeah, got it.
Yeah. Yes. So, so this need not be labels alone. I mean, I can also talk about continuous values as well, but that is like an extension. In this talk, I'll only restrict myself to mostly segmentation tools.
Yeah, that's fine.
Okay. So what does Power Watershed framework do? So instead of working with this optimization problem directly, so this is like a single optimization cost function. So instead of working with this cost function alone, what we do is we kind of create a sequence of cost functions. How exactly would I do that? I raise this first term to integer powers this way. And then now I have a sequence of cost functions. And then instead of working with, trying to find the minimizer or minimizers of a particular element in this in this sequence, I want to investigate what happens in the limiting case. Meaning, so if my x superscript p is the minimizer of cost function q superscript p, I want to find out what the limit of these minimizers gives rise to. So there is some theory behind this on why we want to do this. I won't get into that, but mostly the practical aspects of it. So we are going to investigate how the limit of the minimizers of this particular sequence is going to help us. So it so happens that practically the limit essentially depends only on the relative ordering of the edge weights. So as of now, this is not clear as to why it happens. In a couple of slides, when I mentioned the algorithm to actually compute the limit of minimizers, the reason as to why this property holds would be very clear. One thing that you might ask, although not all solutions which are contrast invariant are useful because I can always give a simple constant solution which is kind of not useful at all. But then the second property essentially tells us the limit of minimizers is actually quite close to minimizing the original cost function in most of the cases. So this is not an exact result again, but then for the application point of view, from the application point of view, the results that I'm going to get would be quite desirable. So these are in fact very close to what I would have got if I had directly minimized the original cost function. And the advantage that we have here is instead of, so the computations would be much faster because of the way we design the algorithm. So that part again would be very clear. But for now, take my word that so instead of working on the image graph as a whole, computing this limit of minimizers, it only requires a substructure of the image graph. And that substructure, we call it as a union of maximum or minimum spanning trees, depending on what I use to model the edge weights. If I had used similarity to model the edge weights, I would be working on union of maximum spanning trees, and similarly the other case. So this in practice would be this would have much lesser number of edges when compared to the image graph as a whole. So what exactly do I mean by this union of maximum spanning trees? Let's have a look at a small example so that things would be clearer. So here, as you see, on the left side, again, this is a fictitious image. I have edge weights, and these edge weights correspond to similarity between the adjacent pixels. Meaning, if the weight is high, then these two are highly similar, and if the weight is low, these are not very similar, and so on. So a union of maximum spanning tree is nothing but I take all the edges. So any edge that belongs to at least one maximum spanning tree of this graph, I take a union of all such edges and then construct the induced subgraph. So obviously, since since this original graph is connected, in the induced subgraph, I'll have all the vertices as usual, and then so this is like so this contains all the maximum spanning trees essentially. So this, as you see here, this doesn't have a fixed number of edges. It depends on how the edge weights are distributed. But in practice, most of the cases, you would definitely be able to reduce the number of edges when compared to the original image graph. So, so this is like you have reduced the computational burden because you are working on a much smaller set of edges. So let's have a look at the algorithm now. So before looking at the algorithm, let's look at what the power watershed solution and how we would compute it. So recall that I looked at a cost function of this form, and then I raised it to integer powers, positive integer powers, and then so now since I am working with finite graphs, I have finitely many edges here. So what I do is I rearrange all the terms in the summation, and then I start with the highest weight term. So since my f was an increasing function, I'll just go back a couple of slides. So f was an increasing function. So I just reorder all the terms here with respect to decreasing order of edge weights. And then I write it as a finite sum. So this can be written this way. So now what I would do is observe that in the limiting case, that the terms which are of higher weight, they are going to dominate the cost function. So if at all I want to minimize this particular cost as my p is larger and larger, what I want to do is first I need to concentrate on the terms with higher weight term as coefficient. So this is what we do. And using this intuition, in fact, one can show that this particular algorithm, simple algorithm, can give us the limit of minimizers. So what I do is I start with the, so here I ordered with respect to increasing order. So I start with the highest edge weight, which is I equal to L. And then I start with the entire solution space. First is I compute the minimizers at level at the highest level first. So what I do is at weight WL corresponding to this term, I have QL of X. First is I minimize that particular cost function, and then I look at the subspace of all the solutions that I have there, and then I I restrict my solutions to that particular subspace, and then I go to the next level. So I do it likewise, so on and so forth in a nested way. And then in the end, I return solutions that correspond to the lowest level. So again, so this is a very simple generic algorithm, but the downside is that this is not a plug and play thing, meaning depending on the kind of cost function that I'm working on, I need to, so this is like a generic algorithm, but in order to implement it, you need to have a few more details. But let's take a look at a simple example to understand what I meant here. Say, suppose I have, say, only two levels of weights. So I have a cost function here and a weight associated with that, and then a cost function here and a second weight associated here. So the first weight is less than the second weight. Let me call it W and 2W, first and second. So if I have to compute the limit of minimizers as p goes to infinity, if I do a direct computation, I obtain these points for every p. So I can simply take a limit here and then I observe that the answer is half comma half. But if I want to apply the algorithm and see what happens, so what I do is first I take the higher level cost function. So this is corresponding to the higher weight, highest weight here. I mean, there are only two here. So first I look at this particular cost function, which is this. First I look at this cost function and I minimize it. So now I am on the subspace of solutions which minimize this cost function. So this is all values such that, I mean, this condition is satisfied. So next what I do is at the second pass, I look into this particular cost function. I restrict my solutions to this subspace and then try to minimize this part. So now that I know my subspace is on this, all I need to minimize is, I mean, something like lambda minus 1 whole squared plus lambda squared. I know that when it would be minimized, and this would be the same answer as that of direct computation. So this is just to get an intuition of what is going on there. But yeah, so now I want to just go back here. So now observe that, so the way I'm computing the limit of minimizers, I am only taking into account the relative ordering of the edge weights. So irrespective of what the weights are, as long as the relative weights are same, this is going to give me the same answer. So this kind of answers my question that I was expecting contrast invariant solutions as in here. So this is something that I want, which is being satisfied. So now let's have a look at some of the applications which actually show that this is quite powerful. Let's, yeah. So the first of the applications is that of random walker. So this was done quite a long ago, about 10 years ago. I mean, the original paper on random walker was much older. It's in 2006. So the random walker is a very simple algorithm. So suppose, say, now I want to do an image segmentation, but I have some kind of a prior information, meaning I know for a fact that some of the pixels in the image, as you see on this left image, you see that there are two colors here. One is red and other is blue. So I know for a fact beforehand that some of the pixels correspond to a particular object. So the goal of the random walk is that, okay, not random walk, but in general, the goal of a seeded segmentation is that given that I have some information about the labels of certain pixels, how do I propagate these labels to the unlabeled pixels? So random walker is one of the classic approaches to solve this seeded segmentation problem. What they do is they construct an edge-weighted graph again. So as you see on the left side, these edge weights are some kind of similarities between the adjacent nodes for every such edge. So what the random walker does is for every unlabeled node, we propagate random walks to each of these colored labeled nodes, seeds. So what we do is, as you can see on the middle figure, suppose I start at pixel labeled, at pixel labeled 1. So this is not the, okay, so this is not the label. So this is just to identify this particular pixel. So this is an unlabeled pixel. The labels are actually the colors. So if I want to propagate a label to this particular node, what I do is at this particular stage, I have like two options to walk. One is to the right side and other is to up. So looking at the similarities, I provide some kind of probabilities by taking, I normalize these weights and then, so here I have 2/3 chances of taking this path and 1/3 chances of going up. So likewise, I do it at every every location, and then in order to obtain the probability that this particular pixel will be labeled blue would be I send random walks from this particular pixel to all the seeds that are blue labeled. So here there is only one blue label, which means I take all the possible paths to go here, and then I add up all these probabilities. So this in theory would be the random walk probability. So similarly for the other label, I do a similar thing. So although this is theoretically okay, so how exactly would we compute this? Again, this is very well known that this random walker, obtaining the random walker labels is nothing but a cost minimization problem, but a constrained cost minimization problem. And in fact, it is well known. I won't go into the details of that, but it is well known that in order to obtain these probabilities, it is enough to solve a particular set of a linear system of equations. So this was the original algorithm. But then, so 5 years later, after this particular paper was introduced, it was shown using the power watershed framework that instead of working with the edge weights directly, if I reframe the question as, working on the sequence of these minimization problems, I can obtain much faster algorithm, but the results would be similar. So how exactly would it look like? Let's take a look at again a small example on how it happens. Suppose say here I have like say again two red color seeds and one blue color seed. If I want to propagate labels to the other unlabeled points, what I do is first, since I work with the highest weights first, so here notice that the highest weight is 13. So first, when I look at the cost function, it only contains edge weights which are 13 or 13. So there is only one weight here. So if I have to propagate the labels, so my 8 will be labeled red. So after the first pass, essentially this is kind of labeled red. Now I look at the next highest weight, which is 10. So again, there's only one edge here. So what happens is at the second iteration, my 9 also gets a label red. But then in the next level, what happens is, so I have the next highest weight is 3 here. So there are like more than one edges of weight 3. So here is where now on this particular collapsed graph, now using only this edge weights of 3, meaning I'm only working on this particular subgraph, 4 nodes, 3 edges. On this, if I obtain a random walker, whatever probabilities I get, I assign this label, that label to this particular node. If the red was higher, I give it a red, or if I get a blue, I give it a blue. So this way, the advantage here is instead of working on the bigger graph at once, I am splitting it into smaller sub pieces, which can be handled. Which can be handled easier. So one thing, although it's like so it's a sequential process. I can't do it in parallel, but even then it's much faster than doing it on the whole graph at once. So this was the first of the applications, and this is what motivated us to look at more applications. So let's move on to a second application, which is what we have done. We have so this is again another kind of segmentation, image segmentation. So the isoperimetric segmentation is a classic heuristic people use to obtain good image segments. So the idea here is now I don't have any prior information on the labels of any of the pixels, but I know some kind of similarities between adjacent pixels. So the idea is that assuming that I have only 2 objects in the image, just for the sake of simplicity, I want to break the whole graph into 2 pieces by removing certain edges such that the removed edges add up to as less as possible, the sum of the weights. And also I want the components to be not too small. So this is to avoid the fact that I don't want to just simply remove a noisy pixel and say that that is an object. So that's the reason we have this denominator term. So this is like saying that if my one of those 2 obtained components are too small, the cost would be high because I have a minimum of these 2 things here. So this is to avoid what is called a small cut problem. But unfortunately, this obtaining an optimal solution to this is kind of NP hard. So what people do is they try to pose it as a, I mean, do a continuous, solve the continuous relaxation, relaxed version, and then obtain a heuristic approximation. So, so this particular cost, as you see here, the sum of edge weights passing through, I mean, so such that the one end is in one component, the other end is in the other component. So this can be written as x transpose Lx, where my xi's are the labels. So if xi is 1 for the node belonging to the component and 0 for the complement, then I can write the numerator as x transpose Lx, where L is the graph unnormalized Laplacian. So this is simply the degree matrix minus the adjacency matrix. So this part is, I mean, very well known. I mean, you can just check it in case you don't haven't seen it. So, and the denominator, I can simply write it as x transpose 1, and this 1 is a 1 vector. So this is simply the number of nodes in the A and A complement. So in order to, when I pose this as a continuous relaxation problem, so instead of looking at only, I mean, constraining my xi's to be only being two discrete values, I allow them to be taking any value, continuous value between 0 and 1. But then the problem with this would be, I'd be getting, so in the end, when I minimize this cost function, I'd be getting values which doesn't directly translate to which object it belongs to. So what people do here is, after I get solutions, say, I mean, if the answer is like 0.2, 0.3, and 0.1, I take a threshold at every level. So say, if I threshold it at 0.1, my answer would be 1, 1, 0. And similarly, if I threshold it at 0.2, the answer would be 0, 1, 0, and so on. So meaning, I mean, after I get a final solution by minimizing this continuous optimization problem, I threshold it at each of the levels and then pick all the solutions and then take the best of all of them. Meaning, I mean, I take all the thresholds, substitute it in the original cost here, whichever minimizes the cost, I mean, among those things, whichever minimizes the best, I pick that and I say that this is a heuristic solution to the original problem. So this is what they do. So this is a small intricacy, I won't go into that. But so essentially solving the continuous problem would boil down to solving another set of linear equations. So this is the classic way people solve isoperimetric partitioning. And in one of the articles that motivated us, the author says that it is enough to solve it on a particular, I mean, on a arbitrary maximum spanning tree instead of using the whole image graph. So this kind of motivated us into looking into why this happens. And we could theoretically show that, in fact, the power watershed solution would be nothing but solving this system of equations, not on an arbitrary maximum spanning tree, but the union of maximum spanning trees. And upon further investigating what the difference between our the exact power watershed solution and this approximation one is, we looked at the solutions, and then in fact it turned out that our solutions are much more robust when compared to the solution suggested by the paper that uses an arbitrary maximum spanning tree. So so here, as you see on the left side, so this this particular plot here, each color corresponds to a particular image, meaning, I mean, if I so on the horizontal axis, the solutions, the x values corresponding to this blue are the normalized values that I get after I solve this particular equation on the original graph. And then on the y-axis, the values are the normalized values, xi values that I get after solving it on an arbitrary maximum spanning tree. So if the plot were perfectly increasing, that means that the solutions would be consistent. So it so happened that, so this is a database with a large number of images. We figured that the solutions by solving the matrix, I mean, the linear system on an arbitrary maximum spanning tree versus the original image graph, they are not agreeing with each other. On the other hand, our solution So this is slightly slower than doing it on an arbitrary maximum spanning tree, obviously, because this has slightly more number of edges. But then the advantage is that these are consistent with solving the linear system on the original image graph. So this is a good thing, because so this is like having a trade-off between good solutions and the speed. So definitely we could reduce the speed, because on an average the number of edges that we could reduce were about 20 to 30%. I don't have that plot here, but yeah, but we could reduce it to from up to 20 to 30%. On the other hand, a maximum spanning tree reduces it by 50% in case of 2D images, but the solutions are not reliable. So, as you see on the right side, this is the box plot of the number of inversions, fraction of inversions that I have. Our solution, the number of inversions are much lesser. And although it appears like a strictly increasing plot, there are some inversions here. Meaning not consistent with the original solutions. On the other hand, solving it on an arbitrary maximum spanning tree is no good. This has a lot of inconsistencies. So this is where it's kind of helpful in speeding up, scaling up the algorithms which are popularly used by exploiting the contrast invariance. So maybe, yeah, okay. So the next application that I want to talk of is that of graph cut, but then which has both similarity and dissimilarity edge weights together. Meaning, suppose now again I'm interested in the image segmentation problem, but now instead of just working with pure similarities or pure dissimilarities, so on the left side, as you see here, so this image has two types of edges, the ones that are colored black and the ones that are colored red, and there are numbers on top of those edges. So here, what I mean by red color edge is, I know with this much confidence that this pixel the pixel identified by 2 and pixel identified by 3. So these 3 pixels, I know for a fact that with this level of confidence, they belong to different clusters or different segments. Similarly, if I have a black color edge, I know with that much confidence that they belong to the same cluster. So this is like I have different kinds of information built in the graph. Then if I want to obtain a good graph partitioning, then a necessary condition that I want to have is something of an unambiguous partition. Meaning, so I want to remove certain edges here, like a simple graph cut, but then the resulting graph should not contain cycles of this form. So by this form, what I mean is they should not contain cycles with exactly one red color edge, because this is like self-contradicting the clusters. So here I'm saying that I know confidently that my 12 and 13 should belong to the same cluster, and then 13 and 8 should belong to the same cluster with this much confidence. Similarly, 8 and 7 with this much confidence. And now I'm saying that 7 and 12 should belong to different components. So that is like, that's negating our own logic. So that's the reason, I want to break this, remove certain edges in this graph such that in the removed, after removing the edges, I should not have any cycle with exactly one red color edge. If there are two red color edges, that is okay, because effectively I'm saying that there is no contradiction there. So these are the things. This is just an intricacy, but solving this is kind of a, this is called as a multi-cut problem, and this is NP-hard problem. Another group has actually proposed a greedy approximation solution to this multi-cut problem. So what they did is they, subject to this constraint that I just mentioned, the cycle constraint. So minimizing these cut edges is same as minimizing the negative of the remaining edges. This is because the sum of edge weights is constant, because I've already fixed the graph. So when I pose this problem this way, this is just a mathematical way to, I won't go into the details, but the basic idea is I want to remove edges subject to this cycle constraint such that the remaining negative of the remaining edges should be as less as possible. So unfortunately, this is NP hard, and the authors in this particular group, they suggested a greedy approximation algorithm. What they did is they add edges greedily with respect to the confidence. So irrespective of whether or not it's a dissimilarity or a similarity edge, they just simply sort them all in the decreasing order of weights, and then they keep adding the weights greedily, subject to this cycle constraint again. Without violating this cycle constraint, they keep adding. In the end, after whatever they obtain, they simply remove all the red color edges. And then whatever they are left out with, now I have several connected components in this, the final solution that I get. They declare these as the components. So this particular algorithm turned out to be very good in the sense that this gave state-of-the-art results on a particular image database, a popular image database. So we figured out, okay, so this is what is the reason why this greedy approximation is giving really good results. So it turned out that this particular greedy solution is in fact the power watershed limit, meaning, it's the limit of the minimizers. If I change the, if I pose this question as a sequence of minimization problems. So what I do is, again, the same thing. I won't go into these details, but essentially I break the original graph into several subgraphs, starting from the highest weights. So once I do that at each level, I break all of them into several levels with, since I'm working with finite graphs, I'll have only finitely many distinct edge weights. I break it into several pieces. So once I break it into pieces, each piece is no longer NP hard because all the weights in that particular piece is same. So it is essentially trying to maximize the number of edges, minimize the number of edges that I'm going to add, I'm going to add at each level. So this is no longer NP hard, and this becomes a simple greedy solution. And this we do it recursively. We start with a particular solution, and then I take those edges, and then I keep adding them to the next level, and so on. So I'm not going into all the details, but the basic idea is instead of working with the original graph, I can do it at level by level, and then keep adding the edges until the last level. So that's the basic idea. How much time do we have?
About Sravan, you have about 10 minutes, 10 more minutes.
Okay. So here is another application. So this, I won't go into these details. So this is a work that I co-authored. Spectral clustering, we all know that it's not scalable, meaning that if I want to do a spectral clustering on graph, again, this is like a image, I can use it for image segmentation without any knowledge of any seeds or anything of that sort. If I just purely know how similar adjacent vertices are, say as you see on this left side graph, the highly similar ones are color coded in blue. Very dissimilar ones are color coded in red, and the mediocre ones are color coded in green. So if I want to do a spectral clustering on this, as the size of the graph increases, an order of n power 3 by 2 algorithm, that's the classic algorithm, classic approximation. This is again a ratio cut is again a NP-hard problem. So that particular classic approximation is not scalable. So what we did in this article is using the same power watershed idea. We kind of, I know obviously for a fact that these two nodes, even if I do heavy computation, I know that these two will end up in the same segment. So in this particular article, what we did was we figured out a formal way to merge some of the nodes. And then once I merge that, the edges, the weights to the other edges that go to at least one of these two nodes, I don't know what to give and so on. So we figured out a formal way to assign edge weights to these particular edges on the collapse graph, such that spectral clustering on this collapse graph would be giving similar results as that of spectral clustering on the original graph. So this is again an interesting work. I won't go into these details. So I'll probably, I'll go to the next application, which is that of image filtering. So these are like several image segmentation algorithms where we could see that simply using the fact that if I break it into several pieces, I can scale the algorithm up without losing any, compromising any the quality of the solutions. So this is like a very useful. It turned out to be very useful, and I believe these ideas can be extended to other data as well, because as you see here, there is nowhere I'm using the fact that I'm working with images. As long as I can construct a graph by assigning weights that make sense, similarities or dissimilarities, depending on what I have, I would be able to translate these ideas. So that's the basic takeaway that I wanted to say here. So let me just quickly move on to the filtering part. So filtering, again, I won't go into all the details. I don't have much time. So, but the basic idea is, image filtering, a classic way is, I mean, all of us know the simple box filters, meaning, I mean, if I want to do a low pass filter, people, I mean, the simplest thing one could think of is simply take a window around a pixel and then take a simple average. But then that won't work well because the boundaries would be blurred. So the idea is that somehow I want to do a edge-aware filtering. So in order to do edge-aware filtering, what people do is now I work with gradients here. So the weights that I have here are some kind of dissimilarities. So meaning, I mean, here you can see that there are two colors of the nodes. One is yellow and other is green. So you can think of these green colored pixels as pixels of one object, and the yellow is the other. So if I want to, so as you can see, the weights corresponding to this connecting different objects, they are high. So these are kind of dissimilarity measures. So the idea is that somehow I take a weighted average filter by not considering the direct number of edges, but then I take the shortest path. So if I want to consider a weighted average filter, the weights that I am going to give from I to j would depend on the shortest path that I have from I to j. So instead of going directly this way, I mean, this is like 1 plus 10 plus 2. So this is the shortest path from I to j. So what I do is I take this number of hops that I do on the shortest path, and then I simply construct a weighted average. So if I want to do a pixel, so the filtered value of the shortest path filter at pixel I would be nothing but the pairwise weight. I mean, so this is like a weighted average, and the weight that I get from pixel j to pixel I would depend on the number of hops that I need to take from pixel j to pixel I. So also it depends. So this bottom is simply a normalizing constant, so as to make sure that these weights add up to 1. So this is a problem with this is it's a very expensive algorithm, because shortest paths, if I have to compute it for all pairs, for all I and j, it's very expensive. So it so turns out that independently another set of authors, they so they proposed what is called as a tree filter. So this we figured that this tree filter is nothing but it's actually a power watershed approximation to the shortest path weighted average filters. So how exactly is this happening? I'll simply take you through the intuition. I won't go into all the details. But the basic idea is that, so instead of working on the number of hops on the original image graph, what these authors did is they simply used a minimum spanning tree of the original image graph. So on this minimum spanning tree, now I notice that between any two pixels, there is a unique path and from one pixel to other, and all these hops can be computed very easily. And so this is like there's an efficient algorithm to do this. So this can be done in linear time. In fact, this gives quite reasonably good results, and we tried to figure out why. And it so happened that this is like a so this is like a approximation to the exact limit. So the exact limit, in fact, it depends on the union of minimum spanning trees that I have. And so looking at this, we could figure out two other ways to do an approximation on this. So it turns out again that computing this is a bit expensive, even on this. So we figured out a couple of two other approximations to the exact limit. And one of those two approximations that we proposed, it does better than the tree filter that was proposed earlier. So in fact, if we look at the results, I mean, it's not significant, but it is slightly better. So there are some images that we used and with several standard deviations and so on with a salt and pepper noise. And one of our approximations did slightly better than the tree filter. And so this is a bilateral filter. This is kind of a baseline that everybody compares with. So at that time, now things have changed. So we compared it with these two standard. Since this is the one on which we built, we figured that ours is slightly better. And here is another plot which shows that. So this is like structural similarity indices. So this is like how similar is it to the. So we started with some nice images, added some noise by ourselves, and then we compared the final filtered images with the original ones which we started off with. And the structural similarity essentially indicates how close we could get it to with respect to the original. So the values that I see for our filtering, these are slightly better than the tree filter. I mean, it's not significantly much, but it's slightly better. And in fact, there's an added advantage to our filter is that we can parallelize this algorithm. So we didn't do it, but we left it for the future work. We haven't, yeah. So this can be done in principle. So yeah, so to summarize these ideas, I mean, so one can scale up several algorithms, mostly image segmentation algorithms that are based on cost optimization on graphs. So these cost optimizations and they form a very large class of. So the class that I described here, that's a much large class, and then a lot of graph cut variants can be speed up using this particular framework. In fact, I mean, if I have a very specific kind of cost, the pairwise cost that I mentioned, it's enough to work with a substructure of the original graph. So this is I mean, so this is actually very useful in the sense that, I mean, so this essentially encodes the required information for the segmentation. So this can be applied in other ways as well. I'll come to that in a while. But yeah, so but the only downside here is this is not a plug and play. I mean, I can't just do it very easily by simple plug and play, because when I work with segmentation algorithms such as spectral clustering, how exactly would I translate the solutions of the upper level to the next level? It's not very obvious. So this part I didn't get a chance to explain it clearly, why exactly it's not plug and play. But yeah, that's one downside to this. But the main advantage is that I can, with little bit of working, I can scale up several classic algorithms. And this is in fact useful in the sense that, so these days, many of these classic algorithms are being learned end-to-end. So for example, so there is this random walker end-to-end learning. It's a recent article, not very recent, just 2 years old. So this for this particular end-to-end learned segmentation algorithm, one can use this idea of I mean, of the fact that, I mean, it depends only on a substructure, and at the test phase, if I can use this for use this substructure, I can speed up the testing results. So this is one way to go about. In fact, many more algorithms are being learned end-to-end. I didn't mention it here, but this is one way to use these ideas. Another way to use this substructure idea is that, so recently, so there is one article called as uniform manifold approximation and projection. So this is called as commonly known as UMAP. So this is a dimensionality reduction technique that kind of preserves the local distances in some sense. So we can, so one way that we are, one thing that we are exploring currently is, can we use this structure to preserve the distances? I mean, so this is like, I don't preserve all the distances, but only these distances, if I preserve, would I be able to get good representations? So this is one area that we are currently exploring. I believe this would result in really good results, given that this particular structures turned out to be containing the most relevant information. I'll stop here. Probably I'll take questions.
Yeah, Sravan, you have, thank you, Sravan, for a nice talk. You have a couple of questions already.
Yes. Okay. So, okay. So, okay. So which slide are we talking here?
So I think your fifth or sixth slide, Sravan, I mean, where you were showing the cuts. Yeah, I think maybe a couple of slides down
Okay.
here
Here.
you present. No, I think one slide up where you're showing the cuts.
Okay,
Here,
cut,
here.
cut. Sorry. Okay. No. So sorry. So, the cuts, I think it came at isoperimetric. That's a bit
For
down.
that, I mean, so basically the question is regarding flooding.
Flooding. Okay. So. Okay. So.
Am I audible? I can
Yes.
clarify the question.
Yes.
Yeah, and I think no, it's just a semantics, right? I mean, you're saying it's a power watershed algorithm, right? In a typical watershed, you
Yes.
flood, then it's as if you release the floodgate. Therefore, after all the flooding subsides, right? You see the islands. Those islands are supposed to be the objects, right? That's how you
Yes.
kind of metaphorically interpret the segmentation technique, right? So
Yes.
in your case,
Yes.
you are actually varying that particular p, right? As p tends to infinity, that's when you're saying that it's sort of like that's what you're trying to seek, right?
Yes. Correct.
In terms of equivalence, does it what it means? No, but you mentioned that p should be integer, right? I don't know. I thought p is equal 0, which means that no, every weight is equal, right? It's basically 1. You don't really care about what.
Yes.
So
Correct.
that's how you are progressively increasing the p. Equivalent to the plain classical watershed algorithm is that you're releasing the floodgates. Eventually, those islands formed in the context of image segmentation. I think you'll actually end up with image segmentation. Is that what it is? I mean, what is the that's the context in which I was asking that. But
Okay. Yeah.
it's
So
a stretch
this is.
metaphor. That's okay.
Yes. Okay. So I think I understand your question. So by varying p, essentially I'm getting different kinds of segmentation algorithms. So in fact, if I take my p equal to 0, that is as good as saying that all weights. I mean I don't care. I'm indifferent to all the weights.
Yeah.
And I mean if I set p equal to 1, it turns out that it's kind of a simple graph cut is what I get. And I mean for p equal to 2, I mean we get something close to random walker, and p equal to infinity, we get something like a shortest path based.
Oh,
So
very interesting.
yeah.
Oh, it's
So,
not a simple like a watershed interpretation, right? It's something lot more
yeah,
than.
it's something more than that. Actually, you can probably check this particular article. So this gives that. Sorry, just a moment. Yeah. So this article.
Okay.
So this article contains all the. I mean, by varying p, what kind of results I get is
Oh,
mentioned here. Yes.
okay. It's like even though norms look very similar in terms of the raised to the power of p, but they get very different behavior, right? It's something like that. Yeah.
Yes. Something of that sort. Yes.
Okay. Thanks.
Yes. And okay, the next question is.
Next question is, as you are, let's say, progressing and iteratively solving it, right? When the remaining edges, will they remain connected, or should they remain connected? In other words, are your constraints like when you say it's a segmentation, right? Are you
Yes.
looking for closed objects, or like orphans are all okay too?
So closed objects, mostly closed. I mean, orphans, we won't end up with orphans. The reason is, in the end, since the original image graph is connected, by the time I loop through all the edge weights, I will end up assigning it to one or the other.
Okay.
I mean, implicitly it's done. It's not an explicit way of doing it.
Okay. Other is also, I don't know if you have time. Other is, what are the other techniques, for contrast? By the way, it looked like a very nice property that, just making sure that the relative ordering of the edge weights ensures that, you achieve in contrast invariance. In a classical setting, what are the other ways that can be done? Of course, in the deep learning context, I think you can just do data augmentation and expect that invariance is achieved, right? But I guess yours is an unsupervised technique. Therefore,
Yes.
a lot more hard work. It's
Yes. Yeah, I'm not sure. I mean, even I am aware of only, I mean, the classic, I mean, the way people do it, which is data augmentation.
Okay.
Yes.
But I'm expecting that some of your learnings in this thing could be translated into something awesome on the deep learning side. Some of the motivations and inspirations that you get out of this work, I think, I don't know how, but that seems like one direction to think of.
I mean, one thing that comes to my mind, Shoma, is the following: that many a times among the neurons, the connections. I mean, if in a fully connected deep neural network, right? You tend to have some redundant connections.
Yeah.
Right. So I mean, using this technique, whether we can basically, I mean, if there are two neurons across two different layers,
that's a fascinating idea, right?
I mean, that's basically doing the same thing, right? I mean, they're just spatially different. If we can establish such redundant edges, just get rid of those. And I think you can make the neural networks learn faster and more effectively. That's what comes to my mind.
And I think what you're proposing, if I read what you're saying correctly, is that if you think of a neural network itself as like a graph where these edges are actually weights, right, so to speak. Then if you raise them to the power of p, what do you get? What kind of structures do you discover? I think that's a beautiful area. I mean, I think we'll be curious to know how it looks. I think.
Yes. Yeah. Yes.
And also he's using a sort of a distance function which is suited for neural networks as well, right? I mean, if you look at his the subgraphs that he's he's choosing a mean square function.
That's the version you mean. I mean, it must be scalable. That's what you meant, right?
Correct. Right. Sravan, I'm wondering, I have just one question. Instead of the squared function, right? I mean, distance function, can you use a mean absolute distance? Will it change anything?
Okay, so you mean to construct the edge weights?
Go to the, I think, it's the next slide where you are using that.
The X transpose X.
X transpose X, Pij. No, not this. The slide that contains that distance function.
Where did I use distance? On the top?
Yeah. I mean, you just missed it. Just go on slide.
Okay.
Yes. Yeah.
Okay, you mean here?
I mean, does it matter? Will it matter? I mean,
so if it's a convex function, it's easier to handle. Otherwise, it's hard.
Yeah.
But I mean, you just have only one point of singularity, right? Which you should be able to handle. Otherwise, even the absolute distance is actually convex piecewise, right?
Yes. But I think, so that was a bit, so one of my PhD advisors group, they tried it, and they couldn't really handle it, I believe. But I don't know. I mean, it can possibly be done with a little bit of work.
Yeah.
Yes.
I think the analytical niceties will not be present, but
right.
Somewhere else.
Right.
Yes.
Correct. Anyway, at any rate, nice talk, Sravan. I mean, I have actually heard this talk now for the third time. So, yeah. But anyway, nice presentation.
Nice talk, Sravan. Great job.
Yeah, thank you.
You did it very well. Thank you.
Sravan, just one quick question. So, I mean, what is like you talked about contrast invariance, but what about other invariances that are typically there in images as far as classification is concerned, right?
Okay. So
yeah. So what is why did you focus just on the contrast invariance?
Okay. So this was, we picked it up because we felt that this was not touched upon by many people. So rotation and translation, already people are doing. So we thought, how can we handle contrast invariance? That is where we started off with, and then we went on, and then we figured out a lot of results. So we kind of explored into it.
Okay, so it was kind of unexplored. I mean, there was no other kind of motivation for this or intuition for this kind of. I'm just looking at from that perspective.
Okay. We didn't find out. We didn't find any articles at all. In fact, which uses contrast invariance. So we thought, why not we do it?
Okay, I was under the impression that there was some kind of intuition behind this. So That's why I asked this question.
Okay. No, yeah. So it was, yes, it was more like an unexplored thing. So that's the
Okay,
reason.
all right.
Now, Sravan, can you share any link of your papers? I like to read that.
Okay. So this all the papers I can.
Your paper and the random walk watershed. That's
Shravan,
Yes.
I mean,
Yes.
what we are doing now is that for every talk, we are collecting, and anyway, we are recording, right? We are also collecting the slides. So if you email the APPCAIR office and
Yes.
copy to me and Ashwin, right?
Yes.
Then we will upload your slides to the YouTube channel as well. Shoma, we are maintaining just one portal, which is that YouTube channel.
got it.
Right? We are uploading everything there. Okay.
No, this will be extremely useful in some of the applications that we are working.
Yes, of course.
Email segmentation is in a way quite fundamental to object detection, etc. Right? So yeah.
The only thing is that Shravan and his clan are far, far detached from the world of deep learning. So I don't know, I mean, how interested he will be, but we will certainly be very interested. Yes.
Thanks.
So,
Thanks.
yeah.
Yes.
Okay, Shravan, I'm stopping the recording now. Thank you
Okay.
everyone for joining the meeting, and we'll see you next week.
Yeah, thank you, Sravan.
Thank you.
Thank you.